Alright, hello guys. Today we'll be doing a bit more on practice problems with optimization. I picked two that seem to be really weirdly phrased from the textbook. So yeah, we'll evaluate it together. So this first one is a bit of an airplane problem, and I think this is kind of misleading because it starts off by saying the passenger capacity is 300, but at certain times of the year, it's only really 180. So I'm going to do this question with 180 passengers, or the assumption that that's where we start. The next part of this question says that there's a reduction of 10 euros, 10 euros below the price of 500 for every additional 2 passengers. And then it's going to ask us to find the best ticket price. So we'll assign some variables. N is equal to passenger. And we're going to keep it at that. So it's asking for revenue, which you can see right here. Revenue is just the amount of money the company makes. We don't subtract or add anything to it. So if we can express revenue as a function of the passenger size, and we can say, okay, our first condition is 180. That's where we start. And for every additional passenger, or for every additional 2 passengers, the price then becomes 500 minus 2n. 500 minus 10n. So this is the euro, how much you're going to have to pay in euros, and this is the amount of people. So really quickly, we can expand this. So this becomes 90,000 minus 1,800n plus 1,000n minus 20n squared. And if we combine like terms, we see that 20n squared, we get 20n squared minus 800n plus 90,000. So then we can just really take the first derivative and then determine the max, or in this case, the maximum. So dr of n over dn is equal to negative 40n minus 800. Because it's a stationary point, we set it at 0. So we have that. So it's equal to negative 40n minus 800. And I'm just trying to figure out why we have negative 800, because if we evaluate for n, we should get 20. So what I'm going to do is I'm just going to take the absolute value and just say it's 20. So 20 should be the amount of passengers you have. And so the best ticket price then becomes R of 20, which equals 180 plus 2 times 20, 500 minus 10, 20. And whatever you get is your answer. So that's the first question. The second question I kind of want to touch on is this one, because it's a bit more abstract. So I'm going to draw this one out, actually. So we start off 2 kilometers offshore in a boat. So I'm going to draw a boat. Maybe I'll draw it here. So let's say this is my boat, and it says that I'm 2 kilometers offshore. But it also says that this coastline is modeled as a straight line. So I'm going to draw a straight line. And then I'm going to say that this distance right here is 2 kilometers. And essentially it's telling me that I want to reach a town which is 6 kilometers along the coast from the point opposite my boat. So this is the point opposite my boat, and this is going to be the point, let's call it W, that is 6 meters along that, 6 kilometers along the coast. Now, we can row at this, it's giving us rates now. We can row at 2 kilometers per hour, and we can jog at 5 kilometers per hour. So it's then asking us to find the smallest amount of time in which we can make it to point W. So you have two options, really. We're going to have to land this point someplace along the coastline, and let's call this point, I don't know, M. Now, the distance here, we don't know. This distance here, we'll just call it X, because we don't really know where we're going to land our boat along the coastline. M is just some random point for the sake of illustrating this question. So we'll call this distance X. And so this distance, I'll say it in red, then becomes 6 minus X. And so we can essentially find a couple things out. We know that this is a triangle, so then the hypotenuse by Pythagoras' theorem is just 4 plus x squared, all square rooted. And so this tells us a couple of things. We know that if we're on this traveling on this hypotenuse, we're rowing our boat. And we also know we're rowing our boat at a speed of 2 kilometers per hour. These quantities are in km. And we know that if we make it here, then the rest is going to have to be by running, which is the rate for that is 5 kilometers per hour. So then we need to create a function which describes time, or which describes time as a function of x, which is what seems to be changing, or which we want to optimize. So time as a function of x is, first of all, 4 plus x squared, all square rooted km. But remember, we want to find time. So to find time, we divide distance by velocity. So that becomes 2. And then we add our other quantity, which is 6 minus x kilometers, divided by our velocity on land, which is 5. And then we want to find the stationary point such that we're at a minimum. So this becomes d of tx over dx. And then we just take the derivative of this stuff. So it becomes 1/2 4 plus x squared to the 1/2 times 2x. And then this becomes 6 over 5. Well, I'm not going to derive this part. This just becomes, if we expand this, is 6 over 5 minus 1 over 5x. It just becomes negative 1 over 5. And then all we really have is just to set this to 0. Now, I'm a bit too lazy to actually evaluate it, but if you evaluate this expression for x, setting it at 0, which is what we did, you're going to get some value x, which describes this distance right here, in which case you answered it. So yeah, I hope that helped. If you have any questions, please feel free to ask, and yeah, thanks.